So this may be written as tan inverse del u over del y into delta y into time divided by distance in perpendicular direction, which is del y 1 plus del v over del y multiplied by del t. For delta t tends to 0, we have del u over del y into del t, right. So gamma xy, by putting the value of del alpha and del beta in this equation, we have gamma xy is equal to del v over del x and del u over del y. This is the angular deformation, right. Or in simplified manner, we can find out the angle. This angle is equal to this perpendicular distance del v over del x. This perpendicular distance is del v over del x into delta x into delta t divided by this horizontal distance. This horizontal distance is delta x, and change in distance is considered less, so this delta x is cancelled. This is del v over del x multiplied by time. So what is the angular rate? Del v dot is equal to del v over del x. And what is this? Sigma alpha is equal to this distance. This distance is equal to del u over del y into del y multiplied by time divided by this distance af. Af is equal to del y, so del y is cancelled. This will del u over del y into delta t. So in a simplified manner also we can calculate this angular deformation of x size and y size, right. So ultimately we will get net angular deformation is equal to del v over del x plus del u over del y, because this is net deformation. This x direction is getting deformed in anti-clockwise direction and y direction is getting deformed in clockwise direction. So this is deformation. So deformation rate is equal to del v over del x plus del u over del y. This is angular deformation. In the mechanics of solid, we have studied that the shear strain causes the angular deformation. Now we have a term called rotation. This rotation is defined by omega z. Omega z is rotation about z axis. So we have two-dimensional figure here in which we have shown x direction, y direction. In x direction, y direction, how do we define rotation? This rotation is defined as the average. This rotation is defined as, since we have a point here and we have these two sides AB and AD, AB and AD here, AB and AD. Now if we have a angular motion, then AB is moving in anti-clockwise direction. So anti-clockwise direction, it is shown with positive sign. Then this side, perpendicular side, is moving in clockwise direction. So it has to be given minus sign. So for rotation, we have this definition that average angle made by these sides AB and AD at point A is called rotation. So by definition of this rotation, we can say that omega z rotation about z axis at point A is equal to 1 over 2, because it is the angle included by sides AB and AD. So 1 over 2 del alpha over del t minus sign, because this is moving in another direction. So del beta over del t. Del alpha over del t and del beta over del t we have already calculated in terms of the velocity gradient. So after substituting the value of these alpha, this del alpha over del t is equal to del v over del x and del beta over del t is equal to del u over del y. So with the help of these deformations, we can substitute the value of alpha and beta in terms of the velocity gradient in x direction and y direction. So omega z is equal to 1 over 2 del v over del x minus del u over del y. If del v over del x is equal to minus del u over del y, then omega z will be, we substitute here, if these two are same, then it will get cancelled and gamma xy is equal to 0, and omega z is equal to del v over del x or minus del u over del y. So, and when del v over del x and del u over del y both are same, in that case gamma xy will be 2 of del v over del x or 2 of del u over del y, but omega z will be equal to 0, right. So, this can be explained with the help of these figures. So, in this figure number 1, if we have a fluid element A, B, C, D, over the time it gets deformed and it takes this position A, B, C, D, another position, right. So, in this case, if del beta and del alpha both are same and moving in same direction, in that case this del alpha will become equal to minus del beta, and this fluid element is said to be subjected with pure rotation. This fluid element is not subjected to any kind of deformation, so it is called pure rotation. Now, in this second figure, we have del alpha and del beta both are same, right, and this fluid element which is A, B, C, D gets deformed and it takes this position at time t plus delta t, A, B, C, D. In this case, this element is subjected to pure deformation without any rotation, right. Now, after understanding the meaning of translation, rotation and deformation, in fluid mechanics we have combination of these three motion called translation, rotation and deformation. So, fluid flow becomes very complicated. So, to deal with complicated, we have the mathematical formulation as well as some graphical understanding, as well as with the help of some pictures or with the help of some visualization technique, we try to visualize the flow and then we try to understand, then we develop the governing relationship. So, that is why in fluid mechanics it is very important to understand the kinematics with the help of several tools. So, we have a mathematical tools, we have graphical tools, we have geometrical tools, as well as we have some techniques to visualize the flow, right. So, to understand what we will do, we will try to see with the help of few videos. Like in this case, we have the definition of streamlines. What is the definition of streamline? We have already studied. In this case, this fluid flow is made visible with the help of some technique of visualization, in which fluid is flowing through a past cylinder. This is a cylinder, this portion is cylinder and fluid is flowing. If fluid is flowing over the cylinder, then what happens? So, we try to understand with the help of some visualization technique.